Welcome back, everyone. So in this lesson, we're going to talk about attributes of polynomial functions. So we're going to look at more specific characteristics of these equations and graphs. So just kind of starting off with the general equation form of a polynomial. So we have this monstrosity that we have right here, where f of x equals a sub n times x raised to the n plus a sub n minus 1 times x raised to the n minus 1, so on and so on, until we get down to a constant term. So what's going to happen is, in order to look at the specific attributes of your function, we're going to focus on what we call the leading term. So your leading term of your polynomial is going to be the term with the highest degree. And then the highest degree is going to be dictated by your exponent. So you're looking for the value that has the highest exponent value. So my leading term in this case would be a sub n times x raised to the n. And then specifically, we're going to even take the leading term and we're going to look at even the parts of a leading term. So if I want the degree of the polynomial, where the degree is going to refer to the exponent. So that exponent right here is what we refer to as the degree. And then your leading coefficient is going to determine end behavior. So your leading coefficient is going to be the value that's going to be in the very front. So that's going to be your value, which should be a number. So that will be a sub n. So with that, now we're going to take a look at some polynomials and we're going to kind of identify these parts. So if I have f of x equals 3x to the fourth plus 2x minus 7, the leading coefficient would just be the value in the front, which in this case will be 3, and then your degree is going to correspond to the exponent, which in this case would be 4. So now if I look at the next one, so number 2, we have f of x equals 12x minus 7x cubed plus 11. So you first need to identify your leading term. Your leading term, remember, is going to be where the highest exponent is. So my leading term is actually negative 7x cubed, which means your leading coefficient would be a negative 7 with a degree of 3. And then number 3 here. So we're going to have g of x equals just 4. So with this one, this is the same as writing 4 times x raised to a 0 power, which means your leading coefficient, which would be 4, and this is going to be a degree of 0. So now we're going to take a look at the extrema of these different polynomials. So the extrema of a graph are going to be either the minimums or the maximums. I can't spell. Everything's fine. Whoops. So in your polynomials, you can have a combination of both. You may only have a minimum. You may only have a maximum if it's like quadratic in nature. But in terms of extrema, there are just two different types. Now, with the minimums and maximums, we can get even more specific. So we can refer to our extrema as relative, or another way of saying it is just local. And then another way that we're going to refer to these is going to be what we call absolute or even global. So we're going to start with relative. So relative extrema is going to occur just when your polynomial is going to change directions. So if I look at my graph down here, this is our sample graph. So I do want to make some adjustments rather. So if I look over here on the far right side, we do have an arrow, which tells me that this graph is going to go indefinitely down. So I just want to exaggerate that just so that we can kind of get a better picture of it. So looking at this graph, so we're going to have local extrema anytime your graph is going to change directions. Now your local extrema, they can be your endpoints. So in this case, I'm going to say I have a local min at x equals negative 4 and a local min at x equals 0. So at x equals negative 4 and at x equals 0. And then you're going to have a local maximum at these high points. So I'm going to have a local maximum at negative 2 and positive 3. So what we wrote is when the maximum or minimum occurs, but if we want the specific value, then you're going to refer to the actual output. So we have a local minimum at -4, but the actual value would be -3. So we have a local maximum at x equals -2, but the actual value would be 1. We have a local minimum at at 0, but the actual value is -1. We have a local maximum at x equals 3, but the actual value is 2. Now looking at the absolute, or global, is going to be the highest of the high points or the lowest of the low points. So with global, we're looking at the entire function, not just when it changes directions. So once again over here, I'm going to exaggerate my graph. I'm going to draw this arrow to show that it's going down all the way. So when I look at the absolute minimum, I'm going to take a look at my graph over here since it's going down indefinitely. Now, because it goes down indefinitely, it's never going to stop. It's just going to keep going. So what that tells me is we don't have an actual absolute minimum. So in this case, there's just none. Now for absolute maximum, we're looking for the highest point that the graph goes. So I can see that the highest point of my graph would be here at x equals 3 with the absolute maximum value of 2. Our graph does not go higher than that value, which means that x equals 3 would be your absolute max. Okay, moving on. So now we're going to look at your even and odd functions. So with your even and odd functions, these are going to deal with symmetry. So an even function is going to be symmetric over the y-axis. And then an odd function would be symmetric about the origin. So with symmetry, with even functions, this is going to be symmetric, and I like to think of it as kind of a reflection. Whereas over here, for odd functions, I think of this as rotational symmetry. So if I look down here, so I'm going to start with the even function. So if I just draw a vertical line at the y-axis, we're going to have the exact same function, or behavior rather, on both sides of the y-axis. So if I were to take even just this left side and then I reflect it over the y-axis, I would get the exact same thing. And then if I look over here at the odd functions, so what I like to do, so I'll show you with this highlighter. So I'm going to highlight the left part of this, and then with rotational symmetry, what's going to happen, if I rotate this figure 180 degrees-ish about the origin, we get the same shape. So that would be rotational symmetry. So whenever we have rotational symmetry, that is what I refer to as odd functions. So now we did it graphically, so now I want to show you algebraically what it's going to look like. So what's going to happen, a little setup that I like to use. So we have f of x, which is the original function, and then we're going to do a reflection over the y-axis, and then we're going to have a reflection over the x-axis. And we want to see which of these is going to be the same. So let me move these over a smidge. So if my first two options here, if these are the same, what that tells me is that these will be even. However, if the second and the third option are going to be the same algebraically, that tells me that the function would be odd. And then if nothing is equal, then it's just going to tell you it's neither. So algebraically, let's kind of go through these. So we already have h of x, so now I want to plug in and do h of negative x. So for every variable we have, I'm going to plug in a negative x. So meaning I'm going to have 2 parentheses, negative x raised to the fourth, minus negative x squared, and then plus 5. So when I simplify, if I have negative x raised to the fourth power, because it's an even number, it's going to be positive. So this is just going to equal 2x to the fourth. And then over here, I have negative x squared, which is positive x, but positive x squared times a negative 1 is going to be negative x squared, and then plus 5. So now the next thing I want to test is going to be a negative of h of x. So I'm going to put a negative out in the front, and I'm going to write my original function in parentheses. So 2x to the fourth minus 2x squared plus 5. And then I'm going to distribute this negative. So negative 2x to the fourth plus 2x squared, and then minus 5. Now what you're going to do here is we're looking to see, does option 1 and option 2 match, or does option 2 and option 3 match? So if I look at these equations, well, option 1 and option 2 are going to match. So if 1 and 2 match, what that tells me is that the function would be even. So based on this, I know this function would be even. So we would have symmetry about the y-axis. So now I'm going to look at number 2. So this is b of x. So the first thing we want to try is b of negative x. So for every x value, once again, we're going to plug in a negative x. So this is 2 times negative x raised to the 5th minus 3 times the negative x. Now, because we have negative x raised to the 5th, that's going to be a negative result. So we're going to have negative 2x raised to the 5th, and then negative 3 and negative x are going to multiply and give you positive 3x. So option 1 and option 2, they don't match, so we cannot be even. So now I want to test option 3. So we're going to look at negative b of x. So I have negative, and then parentheses the original function, so 2x to the 5th minus 3x. And then I'm going to distribute this negative. So that's negative 2x to the 5th plus 3x. So if I look, I can see that option 2 and option 3 here are the exact same. So if option 2 and 3 are the same, that means this is going to be odd. Now looking over at number 3. So we have a cubic function here, so we have k of x. So I would say take a minute, try this one on your own. So we have k of negative x. So we're going to have negative x raised to the 3rd power plus 3 times negative x minus 1. So when you simplify, that's going to give us negative x cubed minus 3x minus 1. So I want to check to see if the original and then k of negative x is the same. So unfortunately, they are not the same, so it cannot be even. So now I want to see if it's going to be odd by checking 2 and 3. So whoops. Now we need to check negative k of x. So negative parentheses, and then the original. So x cubed plus 3x, and then minus 1. So when you distribute the negative, so negative x cubed, that's a 3. Minus 3x, and then plus 1. So when you look at your results, so 1 and 2 don't match, so it can't be even. 2 and 3 are close, but the ones don't match, so it can't be odd either. So nothing matches, so what this tells me is that it's just neither odd nor even. Ta-da! Now looking down here at 4 and 5, now we're looking at it graphically. So number 4, what I like to do on my iPad is I like to just trace over this first part of my graph. And then what I do is I'll rotate it and see if it overlaps. And it does. So we have rotational symmetry, which tells me that this is going to be odd. All right, and then if I look over at number 5, well, if I look to see if we have rotational symmetry, I would just check this first part right here, but that doesn't work. And then the next part is you're going to check to see if it has symmetry about the y-axis, and well, that's not symmetric either. So in this case, this would also be neither. So over here, I'm just going to copy and paste. we go. So that would also be neither. Now we're going to take a look at end behavior. Now, end behavior is going to be super important. So with end behavior, this is going to describe how a function is going to behave, which I know is so helpful. But another way of saying behave is we're looking to see how the graph is going to move. So when I say how it moves, what we're really paying attention to is we're looking at the value of your y, which is your output. So more specifically, we're looking at f of x. So with end behavior, we're going to introduce what we call limit notation. So your limit notation is going to look just like this. So the way that you would say this is the limit as x is approaching negative infinity of f of x is going to equal then some value. Now, because this is when your x value is approaching negative infinity, this is as it's approaching the left side. And then we're looking to see what's happening to the graph as I go to the left. And then conversely, we can look at the right-sided end behavior. So once again, the limit as x is approaching positive infinity of f of x is equal to whatever that value is. So as the x value is increasing, we're looking to see what's happening to the graph. So we give you these sample graphs over here. So we're going to start off with just number 6. So when I look at my graph, I can see that my graph as I go on the left side is going to be going up, and my graph towards the right side is going to be going down. So I want to focus on just the left behavior and just kind of see what's happening just in English. So as my x values are decreasing, as I go further left, my y values are going to be increasing. So that's essentially what we're saying for English. So as x is decreasing, you could say either y or f of x. I would take either one. So y or f of x is increasing. And then as a limit, what you're going to write, so you're going to start with the limit as x is approaching negative infinity of f of x. That's going to equal positive infinity since it's going up, since it's increasing. So now for the right-sided behavior, so as my x value is increasing, I notice that my y values are decreasing. They're going down. So for this one, so as x is increasing, y is decreasing. And then for your limit notation on this one, so you would write the limit as x is approaching positive infinity, since we're going to the right, of f of x, and that would equal negative infinity, since it's going down. So with this, then I would invite you to try, or pause here and then try number 7. So looking at my graph here, so I can see my graph is going to be going up on both sides of my graph. So for my left behavior, I would say as x is decreasing, y is increasing. Which means as a limit, this would be the limit as x approaches negative infinity of f of x. It's going to be going towards positive infinity since it's increasing without bound. And then for my right behavior, similar idea. So because it's going up, so as my x value is increasing, my y value is also increasing. So what this tells you, so I'm actually just going to skip right to the limit. So in this case, we would say the limit as x is approaching positive infinity of f of x, since we're going to the right, and that's going to equal positive infinity since it's going up. So now with your limit notation, now we're going to practice it with some graphs. So we have 4 different types of graphs, and then we have some algebraic graphs, or some polynomials written below them, which we're going to look at. So looking at this first one right here, so I like to exaggerate my arrows on both sides when possible. So if I look on the left side, it's going down. If I look on the right side, we're going up. So my limit notation here, so for the left side, we're looking to see as it goes this way. So my limit as x is approaching negative infinity of f of x, since it's going down, it's going to approach negative infinity. And now looking at the right side, so as my x value is increasing, my y value is increasing. So it would go up towards positive infinity. So how I would write this one, so the limit as x is approaching positive infinity of f of x is going to equal positive infinity. And then this function type is actually going to have a specific name. This is what we call a positive odd function. So all positive odd functions are going to have this specific end behavior. So over here, looking at the next one, so once again, I'm going to exaggerate these arrows. So we're going down and down. So if I look at this one, so my left end behavior, so the limit as x is approaching negative infinity of f of x is going to be negative infinity since we're going down. And then the right end behavior, so the limit as x is approaching positive infinity of f of x will be going towards negative infinity, once again, since we're going down. And then when you're going down and down on both sides, we refer to this as a negative even. So when I say the positive, odd, or like negative even, the even and odd, this is going to be in reference to the degree, not symmetry. So the even and odd that we talked about up here, this is going to be in terms of symmetry. But down here, when we talk about even odd, this is in terms of degree. So this is referring to the exponent of that polynomial. So for the next one, so now we've got, as we go to the left, it's going up, and then as I go to the right, it's going down. So with this polynomial, or with this graph rather, so my limit as x is approaching negative infinity of f of x is going to be approaching positive infinity since we're going up. And then on the right side, my limit as x is approaching positive infinity of f of x, well, as I go to the right side, we're decreasing, which means we're going towards negative infinity. So this type of graph is what we refer to as a negative odd. So all negative odd functions are going to have the same end behavior on both sides. And last but not least over here, so once again, exaggerate my arrows so you can clearly see them. So when I look at both sides, it's going up and up. So my left-sided limit, so the limit as x is approaching negative infinity of f of x is going to be positive infinity. And then my right-sided limit, so the limit as x is approaching positive infinity of f of x is going to be positive infinity. And then this is what we refer to as positive odd. Nope, not odd, sorry. Positive even. There we go. So these are the 4 different polynomial types in terms of leading coefficient and type of degree. So now below, we're going to look at specific types of polynomials. So there's different ways to kind of analyze and look at these. So we're just going to kind of start off on number 12. So looking at number 12, you're really going to pay attention to the leading coefficient and the degree. You want to know if it's going to be positive or if it's going to be negative, and then you want to determine if it's even or odd. And that's going to be based on the degree. So if I look based on the leading coefficient, I see it's a positive number. And then if I look at the degree, 3 is an odd number, which tells me this is a positive odd. Which positive odd, your graph behavior is going to look something like this. So as x is decreasing, my y value is going to go down. And as my x value increases, my y value is going to go up. So I want to represent that information in limit notation. So my limit as x is approaching negative infinity of f of x, it's going down, so it's going to go down towards negative infinity. And then my limit as x is approaching positive infinity of f of x, as I go to the right, it's going to be going up, which means it's going to go towards positive infinity. All right, let's actually go down to 14. So with 14 here, so you want to first identify your leading coefficient, or not leading coefficient, your leading term, which has your leading coefficient degree. So I can see that my highest exponent is here, so that means my leading term is negative 9x to the 8th. So I see that we have a negative in the front and that we have an 8 for a degree, which means we're going to have a negative even. So negative even, which tells me my graph would look something like this in terms of end behavior. So it's going to go down and down on both sides. So what's going to happen is your end behavior will be, so on the left side will be the limit as x is approaching negative infinity of f of x is going to equal negative infinity. And then my limit as x is approaching positive infinity of f of x will also equal negative infinity. Okay, now let's look at 16. So identify your leading term first. So my leading term is going to be with the highest degree. So negative 10x to the 4th is going to be my leading term. So I have a negative, and then if I look at my degree, we have a degree of 4. So this is a negative even. So negative even is literally just copy and paste of what we did above. So I'm going to cheat a little bit and just drag and drop that in behavior. It's going to be the same thing. All right, so I would say pause here and try 13, 15, 17 on your own. So let's go through 13. So 13 here. So my leading term would be the negative 2x cubed, which means I'm going to have a negative odd function. So negative odd, which means my function is going to look something like this in terms of behavior. So as my x value goes towards negative infinity, my y values are increasing. And then as my x values are increasing, my y values are decreasing. So in terms of limit notation, so I'm going to say the limit as x is approaching negative infinity of f of x. And that's going to equal positive infinity. And then the limit as my x value is approaching positive infinity of f of x, well, that's going down, so that's going to approach negative infinity. So that would be my end behavior here. So now with 15, whenever your polynomial is in factored form like this, you're still going to pay attention to if it's positive or negative, and then you're going to look at the degree. But how you approach the degree is a little bit different. So in the front, you're still going to look to see whether we have a positive or a negative. So in this case, we have a positive. And then in terms of the degree, well, we have a degree of 2 with my x value. And then with x minus 2, that has what we call a multiplicity, rather. Multiplicity of 1. And then x plus 5 is going to have a multiplicity of 1. So for your degree, when it's in factored form like this, you're actually going to add up the exponents together. So 2 plus 1, which in this case is going to be 4. So in this case, we have a positive even. So this will be positive even. So positive even, your graph would look like an upwards facing parabola on both ends. So for your end behavior, as my x value decreases, my y value is increasing. As my x value is increasing, my y value is also increasing. So with limit notation, so the limit as x is approaching negative infinity of f of x, well, that's going to equal positive infinity. And then my limit as x is approaching positive infinity, of f of x, that's going to equal positive infinity as well. Now looking at 17, so we have another factored form here. However, we kind of threw a little curveball at you, and that's because of this last term right here. So before I even start this one, I'm actually going to rewrite. So meaning, I'm going to start with x parentheses x plus 1 cubed, but then I'm going to reorder the last one as negative x plus 1. Now when I get here, I will need to take out that negative. So I'm going to have x parentheses x plus 1 cubed, and then I'm going to take out a negative 1. And when I take out that negative 1 from this last term, that leaves us with x minus 1. And then what's going to happen, this negative, I'm going to move it to the front. So when I move it to the front, it's going to turn into negative x parentheses x plus 1 cubed x minus 1. So I see in the very front we have a negative. Now I need to look for the degree. So the degree would be 1 plus 3 plus 1, which in this case is going to give you 5. So the degree would be 5, which means we're going to have a negative odd. So negative odd could look something like this. So for your limit notation, so as my x value decreases, my y value will increase. And then as my x value increases, my y value decreases. So my limit notation, so my limit as x is approaching negative infinity of f of x, well, that's going to equal positive infinity. And then my limit as x is approaching positive infinity of f of x, that's going to equal negative infinity. So then down below is kind of a quick reference for the end behavior that we just did. So whether you have a positive or negative or even or odd. So you can take a look at this quick reference chart that I made and do with it what you will. So now we're going to move on and we're going to include the attributes that we did before. And now we're going to also include all the attributes that we did today in terms of polynomials. So with increasing, decreasing, we're going to start with just the direction of my graph. So with increasing and decreasing, where is my page? There we go. So I know I'm going to be increasing from A to C and then from D to E. So I'm going to say from A to C and then union, since we have more than one interval, and that would be from D to infinity. I think I said D to E. This should not be D to E. D to infinity. So to make sure I don't do that again, I'm going to exaggerate these arrows. Okay, and then for the interval in which we're decreasing, that's going to be just from C to D. Oh, nope, also from negative infinity to A. I am all over the place today, y'all. So this would be negative infinity to A, then union, then C to D. There we go. And then your inflection points, as you remember, hopefully, is going to be where the concavity is going to change. So in this case, concavity would change at point B and then also at 0. So for inflection points, I'm going to say at x equals B and 0. So when you're looking for the intervals in which we're concave up, we're just looking from negative infinity to that first inflection point, which is B, and then from the next inflection point at 0 to infinity. So these two intervals here are when I would be concave up. So that would be from negative infinity to B, but then also from 0 to infinity. And then when you're looking for the interval in which you're concave down, well, that would be from just B to 0. So a local minimum, so it's going to be anytime we go from decreasing to increasing. So anytime we go from decreasing and then we switch to go to increasing, well, that means we're going to have a minimum. So we also go from decreasing to increasing over here. So we're going to have a local minimum at point A and point D. So at x equals A and point D. So a local maximum is going to happen when you have a change in direction from increasing to decreasing. So the only one that we're going to have in this case is going to be at point C. Now we're looking for absolute extrema. So if you look at your graph is going to go up indefinitely, which means we're not going to have an absolute maximum. But if you look at your graph, we do have an absolute minimum. So the lowest point on the graph is going to be at point D. So the way that you're going to write this, so absolute minimum is going to be at x equals D. And then we have no absolute max. So now for the zeros, so this is another way of asking for the x-intercepts. So we're going to have zeros at A, 0, and E. So x equals A, 0, and E. So now the multiplicities, I know we haven't necessarily talked about this in detail. We're going to get more into this later on. But this is kind of going into the cross, bounce, and wiggle that you guys have done hopefully in Algebra 2. So we're going to look at your zeros. So I'm going to start with x equals A, and then we have x equals 0, and then x equals E. So if I look at my graphs up here, so if you don't remember this, that's okay. We're going to talk about this in detail later on. So if I look at A, we're going to bounce off A, which means it's going to have a multiplicity of 2. And then because I cross through 0, that's a multiplicity of 1. And we cross through E, which means we have a multiplicity of 1 here. So over here, for the multiplicity, I'm going to write these in parentheses. So that would be 2, 1, and 1. And then looking at the leading coefficient, we're looking to see if it's just positive or negative. So when I look at my in behavior, it's going up and up on both sides, which tells me it's a positive even function. So I know it's going to be even, or positive rather. And then we're looking at the degree of the polynomial, and this is actually going to come from the zeros. So the multiplicities will actually help you with this. So if you add those together, 2 plus 1 plus 1, which is going to give you 4. And then for even or odd degree, we already talked about that based on the in behavior. We said that this was even, since it's going up and up on both ends. And then we're going to write the in behavior in limit notation. So when I say in behavior, it's implied that you're going to do limit notation. I shouldn't have to tell you that we're doing limit notation. So over here, the limit as x is approaching negative infinity of f of x is going to be equal to positive infinity. And then the limit as x is approaching positive infinity of f of x is going to be equal to positive infinity. All right, and then looking at a sign diagram, I know we haven't covered this in a lot of detail either, but it's pretty straightforward, if I'm being honest. So I'm going to draw kind of like a number line. And then on the number line, each little tick mark or hash mark on the number line, we're going to label it using the zeros. So all your roots are what we're going to label on your sign chart, which means I'm going to have 3 tick marks. So A, 0, and E. And you want to try to space them out kind of evenly, and you want to give yourself some space on either ends. So that means we're going to have 1, 2, 3, 4 different spaces in which we're going to write our signs. So on either ends, notice how I put the arrows. So the arrow on the left side is indicative of negative infinity, even though I don't write it. And then the right side is going to be indicative of positive infinity, even though I don't write it. So for the sign diagram, we're looking at the position of the graph. We're looking in regards to the location of where my graph is. Are we above the x-axis to be positive, or are we below the x-axis and are we negative? So if I look on the interval from negative infinity to a, if I look at my graph, negative infinity to a, I'm above the x-axis, which means I'm positive. So positive. And then the interval from a to 0, now I'm going to look at that interval. So from a to 0, I am also above the x-axis, which means I'm positive here. And then from 0 to e, so from 0 to e, I'm below the x-axis, which means I'm negative. And then from e to infinity, if I look at my graph, e to infinity, we are positive. We're above the x-axis. Ta-da! So here's a lot of the attributes. So I will let you guys try that second one on your own. So what I did is I actually went ahead and filled it out. There you go. So you can kind of check it as you go. One little note that I did make is, I don't know why on this diagram there is 2 points labeled F. So this lower point over here, I renamed it to point I, and then I kept this point up here as point F. So just keep that in mind as you make your diagram, because having point F written twice can be kind of confusing. All right, and then this last page is going to be calculator stuff, so I'm actually going to do that part in a separate video. So have fun. Thanks for coming to my TED Talk. Hopefully this was helpful. Okay, thanks. Bye.